I would like to start thanking the organizers for the invitation to give this talk, and I also would like to apologize. I have a little bit of a cold, so but because of the help of friends and speedy help of friends and organizers, I should hopefully be able to give this talk without problems. So the title of my talk is Spacetime Action for G2 compactifications in Superspace, and we will be dealing with two main themes. First of all, given a supersymmetric string theory or Mtheory compactification in the supergravity approximation, can it be corrected order by order in alpha prime to give a solution of the corrected equations of motion and supersymmetry transformations? Now, the second topic deals with the question, what is the manifestly supersymmetric and complete space-time action for an arbitrary string theory or Mtheory compactification? Manifestly supersymmetric means I want to write this in superspace, so with off-shell supersymmetry, everything is going to be embedded in superfields. And complete means with all Kaluza-Klein modes included. Now, this is a very classic and obvious question, and in my opinion, this action should have been written down many years ago, probably even in the 1980s. So I'm going to try to convince you that this action is actually within reach, that it's not that complicated. Now, so far what I've said is very general, and to be more concrete, I will be focusing on the first part of the talk on type 2 string theory compactified on G2 manifolds, and in the second part of the talk on M theory on compactified on G2 manifolds. Now, there's nothing inherently special about G2 manifolds except simplicity. So particularly for the second point, M theory, or 11-dimensional supergravity, turns out to have the simplest possible field content we could start with. By compactifying a G2 manifold, we obtain n equal to 1 supersymmetry in 4 dimensions, which is a very standard type of supersymmetry. But the techniques and the ideas I'm going to present can then be generalized to all possible string theories and compactified maybe to all possible dimensions. So let's start with the first point. Now, so here's a vacuum solution of type 2 supergravity. So if we compactify on such a 7-dimensional manifold M, and there's a parallel spinor, then we have a covariantly constant spinor. Then we have some unbroken supersymmetry in space-time, and the metric on M has G2 holonomy. Now, the basic tool to understand spaces on which parallel spinors can be defined are tensors constructed as spinor bilinears. So in this case, we have a 3 form and we have a 4 form, and they're related by Hodge duality. Now, in some sense, such a globally defined 3 form is more fundamental than the metric, since given such a 3 form, we can obtain an expression for the metric in this fashion. So when I will be talking about maybe alpha prime corrections to some space. So I will. So the fundamental thing to solve for are not corrections to the metric, but corrections to the 3 form. So if the metric has G2 holonomy, this form is closed and co-closed. But in general, if the manifold is spin, but this spinor might not be covariantly constant, then we have what is called a G2 structure, and d phi and d psi will in general then fail to be closed. Now, but d phi and d psi can still be decomposed into G2 representations in this way. So these objects tau are called torsion classes, and they will come handy a little bit later in the talk. So just think about them as encoding the same information as d phi and d psi. So let's talk about the leading order correction. So here's a gravitino supersymmetry transformation to order alpha prime to the 0. Now, corrections can always be expanded in a basis in the space of spinors in this way. So A and B are some tensors. So usually we would think about these as written in terms of Riemann tensors, but again, so the metric is not something fundamental, but phi is. So just think about them as maybe functionals of phi. Now, to the leading order correction, there are even explicit expressions for these objects A and B. Here they are. But as I'm going to argue in a moment, these expressions are actually not needed. To prove solvability, all we are going to need are some cohomology conditions I will mention a moment. I will mention in a moment. Now, so let's look for a supersymmetric vacuum. So in that case, we so we want to solve for the order alpha prime cubed of this equation, and I'm going to be careful on putting primes onto objects that are corrected. For example, the spinor is corrected, it receives an alpha prime cube correction, while in this expression here, phi and eta are those of the G2 holonomy manifold. Now, we look for a supersymmetry vacuum, so then we set this equal to 0. And we can use this to set up a partial differential equation for phi prime, for the alpha prime corrected 3 form. Now, note that the first two equations here, d phi prime and d psi prime, these are equations for one single object, because psi is the Hodge dual of phi. The Hodge dual contains the metric in a highly nonlinear fashion. So this means that, so also the equation for d psi is an equation for phi. Now alpha over here and beta, so we can, with a little bit of patience, write them in terms of A and B, and if we want, we can even write down concrete expressions in terms of Riemann tensors if we want, but we don't have to. Now, looking at these equations, it's obvious a necessary condition for solvability is that alpha and beta are exact. And as it turns out to be the case. Now, so I'm going to use this phrase several times now in my talk. It requires a little bit of G2 magic to actually show that that condition is also sufficient. So, to order alpha prime cubed, we can actually check explicitly that these forms are exact. So the partial differential equation for phi prime is solvable. Now, moving on to all orders in alpha prime, it's basically more of the same stuff. So in that case, we can set up a proof by induction over the order in alpha prime. So again, now we look at the order alpha prime to the n of the gravitino variation. The left-hand side contains our unknown, which is the order n of phi prime. There are some forms alpha and beta, which involves phi prime only to an order less than n, so to say the sources. And again, necessary condition for solvability is that these forms are exact. And then this, again, using G2 magic, exactness of alpha and beta is not only necessary, but also sufficient. So there's a solution to all orders in alpha prime. Now I should emphasize the difference between the all orders in alpha prime argument and the argument to order alpha prime cubed. Now, nobody has given us the corrections to the gravitino variation to an arbitrary order in alpha prime. So such a formula doesn't exist. It's too complicated. So this exactness of alpha and beta to any order in alpha prime is something that we have to put in. So we are not going to prove it by computing corrections to the gravitino variation, but the next thing I'm going to do is to translate these conditions into a property of space-time. And later on, we will try to derive this property of space-time from first principles. Now, so let's now come to the second part of the talk. Now, again, so the second part of the talk deals with constructing the space-time action in a manifestly supersymmetric fashion. And this could be studied independently of the first part. But it is this cohomology conditions that we need to solve our differential equations, which give us an inspiration how some terms in the action actually have to look like. So this is why I present part 1 and part 2 together. So here's what we want to do. We wish to describe, this is now the second part, we wish to describe the fluctuations around the background that is like Minkowski space times a compact G2 manifold. And so we want to include all states, massless and massive, so we want the full thing. So this can in principle become complicated, can be scary. So we need some guiding principles. So the first one will be four-dimensional supersymmetry. So we will assemble all fields into four-dimensional superfields. And locality, so we will keep locality along spacetime, that's obvious, but also along M by this seven-dimensional space by letting fields be functions of forms on this internal manifold. So 11-dimensional fields then decompose into many four-dimensional fields. We can have scalars, vectors, and asymmetric tensors, being two fields. So all possible. From the four-dimensional point of view, the system is very complicated. Now, but let's start doing simple things. So we want to take these fields now and write them in a manifestly supersymmetric way. So let's start doing simple things. Let's talk about global supersymmetry. And then I'm going to point out where doing simple things is not enough and where we have to become more sophisticated. So we have coordinates of superspace, and superfields are functions of these coordinates. So some of the simplest superfields we can consider are chiral superfields. So that are defined just in the usual Wess-Bagger fashion. The only difference is now, for example, the bottom component here, so is a complex field, and we let this field depend on a continuous label y. So we treat it as if it's an infinite family of fields. Now, the bottom component is something that I call phi hat here, phi hat plus I c, so the three form with indices on the internal space. Now, this object phi hat to leading order and alpha prime will be our calibration, will be phi, but to higher order and alpha prime, we will need corrections, as I'm going to explain. So once we have chiral superfields, so the next naive thing to do is to write down the obvious maybe action for chiral superfields. So it looks in this fashion. So we can have theta to the 4 terms or theta squared terms. And just to get a feel a little bit of this formalism, so here's, if we decompose this in components, so here's part of the Lagrangian, the one for bosonic fields. Since we treat y as a continuous label, sum over y is like summing over these labels, and we run into functional derivatives. But otherwise, the formalism is completely the same as if we have just discrete number of fields. Now, so what is the simplest? Next simpler thing we can do, well, we can pick a superpotential, and there's actually just one choice, phi d phi. So now supersymmetric ground state, the variation of f vanishes, which tells us that d phi hat is 0 and g4 is 0. Not the game we are playing here. So if we look at this equation to leading order alpha prime, we compactified on a G2 structure space, and we obtain dynamically the information that d phi has to be close to preserved supersymmetry, which is naturally one of the conditions for having G2 holonomy. So to leading order alpha prime, this just says d phi is equal to 0. And comparing with our previous result, this just says that phi hat is related by a field redefinition to phi prime. But the important message to take away from here is that we always have a closed three form, phi hat. That's one of the conditions, one of the cohomology conditions that we needed for our existence proof. So there's always a closed three form. Let's talk about the Kähler potential. The bottom component of our chiral superfields are coordinates of an infinite dimensional Kähler manifold. Now, there are gauge transformations in 11 dimensions that give rise to isometries of the metric. It can be shown, the details are in our paper, that because of this isometry, there's always a closed 4 form. So this is the second cohomology condition that we need for our existence proof. So, needless to say, it would be interesting to derive these conditions, the superpotential, this property of K, from a Kaluza-Klein reduction of M-theory. We envision this as a two-step process. First, we rewrite the action of 11-dimensional supergravity in a form that displays manifest n equal to 1 supersymmetry in 4 dimensions. And then in the second step, we use non-renormalization theorems, should give us an information about how things are corrected in the inverse radius or in alpha prime. Now, for the rest of the talk, I will be focusing in part 1. We do not have the finished result yet, but we have made what I consider good progress, and we hopefully will be able to report on the final result of this soon. So let's talk about the Kaluza-Klein reduction of M-theory. Well, we take the 11-dimensional fields, and we decompose them into a 4+7 split. Here we go with the 3 form and the metric. Also, the symmetries of 11-dimensional supergravity give rise to a series of symmetries in 4 dimensions. Now, from the 4-dimensional point of view, the system is very complicated, many fields, many transformations. But we know it has a simple origin. This is nothing else than 11-dimensional supergravity. So we can hope to get a handle on this. So we, for example, know the complete action for the bosonic fields, so in a form that looks like an action in space-time. Now, I won't have time to describe all the details of this action, so let me just highlight a few terms. There's, for example, kinetic term for the space-time metric. There is there is a potential for the scalars from the metric, the scalars from the 3 form. There is a kinetic term, again, for the scalars from the metric and the scalars from the 3 form. Now, let me emphasize here one term, which is the Chern-Simons term. Now, I won't have time to describe the details about this, so I'm just going to mention something that we did recently. So note that this is anti-symmetrized over all the indices. So it includes all fields coming from the 3 form, the scalars, vectors, and antisymmetric tensors. So just recently, we have put this term into superspace, so we have an action written in terms of super fields with off-shell supersymmetry. So I will just be able to mention this briefly at the end and mention a few references. So let's try not to put. So our goal is to put the whole thing just in superspace. So that's it. Very simple. So we have to accommodate all of this into superfields. Now let's do simple things to start with. So let's look, for example, at the kinetic terms. Well, then we really have to get into the nitty-gritty of this and choose a scalar potential. There's actually just one choice, namely the volume of the 7-dimensional space. So G is the determinant of this metric. Once we promote G to superspace, we have to write. We cannot just write. So we have to write something that is gauge invariant. So we actually have to add a contribution that involves a real superfield that contains the vector coming from the 3 form. Well, now what we have to do is, well, turn the crank, extract the theta to the 4 term. Now we want to compare this with the M-theory results. Again, using some G2 magic, we can write the kinetic terms in the form of the first equation. So it's a bit tedious, but it's no problem. And this thing comes in a form that we can compare with the superspace result, which is the second equation. And I highlight here the terms. Got it. And I highlight here the terms that just agree exactly. Now I needed to do something a little bit more sophisticated. namely to get one of the contributions to work, we need to integrate out an auxiliary field from the gravity multiplet. But otherwise, the agreement is perfect. This also highlights the main open question in this enterprise, namely the pi7 projections come out consistently wrong. So this is work in progress. That's what we are doing right now. Also, I won't have much more to say about this, except that we may have to rethink how the 7 components of fields are assigned into multiplets. And we may have to bring new multiplets into account, like, for example, gravity no multiplets. But again, so this is one of the main open questions. Let's talk about the potential. Well, the potential is fun. It turns out that, again, using G2 magic, we can rewrite it in terms of torsion classes. Now, here this is actually a shortcut, and we can be lazy. Namely, this is nothing else than the scalar curvature of a G2 structure space written in terms of torsion classes. And Robert Ryan computed this in a paper for us, so we can just take over the result. And we can compare this with Superspace results. Now we have to take several contributions into account. So tau 0, tau 1, and tau 3, they receive contributions from integrating out the auxiliary field in the Kara multiplets, but we also have to integrate out D terms, which is the auxiliary field in the real superfield that accommodates the 3-form from the metric. And fair enough, even though these numbers are very complicated, the agreement is precise. So it works perfectly. Now, but this is, of course, so the bottom component of Kara multiplets, so that is that is a complex field, so there's also potential for the 3-form. Now, I have to apologize, I couldn't write anything up about this, because the results actually came in after the deadline for submitting the talk. So it actually also agrees perfectly, so there's perfect agreement, but we have to do a few new tricks to get that to work. So the 27 representation of G2, so that works perfectly, that flows from F terms. The 7 piece, we have to integrate out the D term from the gauge field from the metric. And to get the singlet piece to work, we actually have to integrate out one of the auxiliary fields from one of the antisymmetric tensor multiplets that I don't have much time to talk about. So let me just briefly mention in the last minute something that we did recently. So it is this Chern-Simons term that we did put into Superspace. So it's done in 2 papers. So in the first paper, we embedded the tensor hierarchy consisting of all fields descending from the Mtheory 3-form and the corresponding abelian gauge transformations into Superspace. And we explicitly constructed the supersymmetric Chern-Simons action. Well, here it is. This, of course, has only symbolic meaning because I didn't explain what any of the things are. Again, these are all superfields. Definitions are in our papers. Let me just mention so far we have only used in this talk these 2 terms here, but there's also a whole bunch of additional contributions coming from here. By construction, it gives us, once we decomposing components, the complete Chern-Simons term. It also gives the gauge fields in the 14, those coming from the 3-form also work perfectly. But we're still in the process of evaluating all of these, integrating out all auxiliary fields, and so on. Anyway, in the second paper, we coupled the system to the non-abelian gauge field arising from the metric. So if you are interested in this topic, I encourage you to read the papers. And needless to say, so there still remains some work to be done, but I certainly believe that this action, this one, and related actions from other string theory compactifications to other spaces are within reach. So stay tuned, more to come. Thank you.
We have time for a few questions.
Nigel Hitchens had very nice, elegant action principle based on a metric. It's a functional that you can write in terms of this object S you mentioned on one of the first slides. Does it help in any way of writing the superspace Lagrangian?
I'm not sure. So what it would help for? So I think we actually have all.
Well, for example, killer potential, perhaps a piece of the killer potential could nicely be written in terms of the functional.
What? I mean, we have the killer potential. We know what we're looking for. So so I don't think we need any. It would be interesting to learn about this, but so far. Our main problems are somewhere else, the 7 representations. We know what the killer potential is. I mean, it would be interesting to explore it if there's some connection. But at the moment, I do think we have all help we need.
If there is no more questions, let's start again.